Alright, from here we're going to start looking at reactions of alcohols. And while there's a large number of reactions that involve alcohols, we're mainly going to focus on three reactions here. And those three reactions that we're going to look at are acid-base properties of alcohols, dehydration, which as we'll see is essentially the opposite of hydration, and oxidation. And so these are the three that we're going to focus on. So let's start by looking at some of the acid-base properties of alcohols. So when it comes to how acidic alcohols are, the answer is that most alcohols are of moderate acidity. I'm talking about pKa's in the sort of 18 to 20 range. And what this means is that they are slightly less acidic than water. And so if you want to deprotonate most alcohols, you need a relatively strong base. And things that we could use are things like sodium hydride, Na plus H minus. That's the conjugate base of H2 of hydrogen gas, which has a pKa of 35. So a relatively strong base, not quite as strong as some of the things we've talked about previously, like if you remember the video I showed you of tert-butyllithium, the substance that spontaneously catches fire when you expose it to air. Not quite at that level, but still a relatively strong base. So with something like that, you can deprotonate an alcohol like ethanol and make an oxygen anion. There is one type of alcohol, though, that does have pretty good acidic properties, and those are phenols. So phenols being aromatic rings with alcohols on them. These have much lower pKa's, and they are relatively strong acids for organic compounds. The reason for that is the conjugate base of a phenol has the O- next to an aromatic ring. And for reasons that we don't really get into in this course, having a negative charge next to an aromatic ring makes that negative charge a lot more stable. What we find is that negative charge can actually delocalize or be shared by the entire aromatic ring. And that's a very, very stabilizing process. So with a phenol, you can use something as simple as sodium hydroxide, and it'll easily deprotonate the phenol and give you an O-. And when you have substances that are this easily deprotonated, it leads to some very useful properties. So typically most organic molecules, and we saw this a little while ago with alcohols, once we start to get enough carbons, 5, 6 carbons, those types of alcohols are generally not water soluble. But when you deprotonate it and you make this into an ionic compound, these are highly water soluble. And so this type of acid-base property is something that you can very, very easily use. If you needed to separate a phenol from other organic compounds, you can change its solubility and get it to go into water as opposed to being in some other solvent. Right, but the other two reactions are where we want to spend most of our time. We're going to start with dehydration. So this is exactly the opposite of the hydration reaction of alkenes that we learned. So hopefully you recall that the hydration reaction took an alkene and with acid and water and heat added the OH to one carbon and the hydrogen to the other carbon. So what does a dehydration do? Well, dehydration takes an alcohol and a hydrogen on the adjacent carbon, and in the presence of acid, water, and heat, gives us the alkene. So it isn't just kind of like reversing the hydration, it's the exact reverse of that reaction. Now, depending on the alcohol, the type of alcohol that we start with, the conditions that we need for this reaction are very, very different. And what we mean is whether we start with a primary, a secondary, or a tertiary alcohol. With a primary alcohol, we generally need to heat it up pretty hot, 150 degrees Celsius, and strong acid. See here, almost pure 95% sulfuric acid. And we get our dehydration to take place. Again, this dehydration is removing an OH group and it's removing a hydrogen on the neighboring carbon. And as we'll show in a minute, having a hydrogen on that neighboring carbon is a requirement for this reaction to work. All right, so what about a secondary alcohol? So a secondary alcohol still requires strong acid, although we can dial it back a little bit, 95% down to 75%, and generally doesn't require as much heat. Still not the nicest of conditions, still overall pretty harsh. And then finally, a tertiary alcohol just requires dilute acid and typically somewhere around room temperature. And that also gets the reaction to take place. So 3 very different sets of conditions depending on what the starting material is. And again, in each case we're removing the OH group and a hydrogen on the adjacent carbon. Now, as we alluded to a moment ago, it is necessary that you have a hydrogen there. So if we tried to eliminate this compound, we have an OH here, but this carbon here, the one that's highlighted in yellow, notice there's no hydrogens at that carbon. And because of that, it can't undergo a dehydration. Alright, so our take home so far is two things. One, we need that adjacent hydrogen. And second, the more substituted our alcohol is, the better the dehydration reaction works. Now, I should also mention there are going to be times where I refer to this reaction as an elimination. Dehydration is a very specific reaction. An elimination is a much larger class of reactions where we remove something from a starting material. So if I refer to this as an elimination, it is the same overall class of reactions. Now, for some alcohols, when we try to eliminate them, there's more than one possible product. And our alcohol doesn't have to be very complicated for that to happen. So here's 2-butanol. And if we're talking about removing an adjacent hydrogen, we could remove that one in orange, which would lead us to 2-butene as the product. But this one that I've drawn in purple is also adjacent to the alcohol. And that would lead us to 1-butene as the product. So is this something we can predict? Is one of these going to be favored over the other? And the answer is yes. In this specific reaction, we get about 80% for the 2-butene and just 20% of the 1-butene. Why such a big difference? Well, we have something that's known as Seychev's rule. Now, interestingly, if you look this rule up, you may find a few different spellings of his name. No one's quite sure how it was or should be spelled. But Seychev's rule says that in an elimination reaction, the more substituted double bond will be the major product. And what we mean by that is if we look at our two possible products from the previous reaction, 2-butene and 1-butene, 2-butene, the double bond has 2 substituents on it, whereas in 1-butene, there's only 1 substituent on the double bond. And so that means that 2-butene is more substituted and therefore will be preferred. Why is it that more substituted double bonds are preferred? Well, in general, more substituted bonds, more substituted double bonds, are more stable. So let's look at a couple more examples. So for both of these, again, it matters where we remove the hydrogen from. And we've got two options. Up here we could remove this one, which leads us to that product. Or we could go to the other side of the alcohol and remove that hydrogen. Same thing with the molecule below. We could remove this hydrogen, giving us that alkene. Or we could remove that hydrogen, giving us a very different alkene. Which one is favored? Well, in the top case, you can see that this structure on the left, the double bond has 3 different groups coming off of it, whereas the one on the right only has 2 different groups. So this would be our preferred product. For the molecule below, the structure on the left has 3 groups coming off the double bond. And let's fix this. Whereas the structure on the right only has 1 group coming off the double bond. So again, the more substituted product wins. Now, one other question that you might be asking yourself at this point. If this is our hydration reaction, and then this is our dehydration reaction, how do we know where we're going to end up? Because if you take the alkene and add acid and water and heat, you get the alcohol. But then if you add acid and water and heat to the alcohol, you get the alkene. And it's not a matter of when you use all the acid up, because the acid here, and this is the case for both reactions, is actually a catalyst. A catalyst, you hopefully recall, is a substance that speeds up a reaction, but overall isn't consumed by the reaction. So in foundations, we talked briefly about equilibrium. Equilibrium is the idea that reactions are reversible. And that's certainly the case for this. So what you end up doing for a reaction like this is you end up having to look very, very carefully at the reaction conditions. And there are certain properties that you can identify and say, this one favors the reaction going to the alcohol, or this other property favors the reaction going to the alkene. And then you sort of use those properties to influence which direction the reaction is going to go.